Swayam Prabha. Digital India. Educated India.
Professor David Shah from Goa University, Taiwan. He will be presenting on basically the main quantitative structure of properties.
Okay, thank you for the organizing committee for us to present the paper here. Actually, the paper was the work of three units. Okay, the Department of Chemical Engineering at Tsinghua University, and Professor Khan from National Union Universities, and also a company called Genetics Generation Advancement. They have a molecular science and Asian Innovation Center. Okay. The previous presentation have documented what is called computer-aided molecular design. We want to have a method that we can actually design a molecule to satisfy a certain property. Okay, and we want to do it before we do the experiments. A good CMAD procedure will consist of two important elements. One is property prediction, how we can predict structures from properties, predict properties from structure. And the other is that we should have a good method to solve the optimization problem, or what we call the structure generation problem. How do we design a new structure? Today we will focus only on the property prediction part. And the property prediction part is usually called the quantitative structure properties relation, QSPR. Okay? What is actually a QSPR is that we can predict, given the structure, the property we design. Okay, we want to build a function that can predict the properties we design given a structural representation. But how do we represent this structure, and what is the functional form of F are the problems of finding a good QSPR. And as many of us know, a very common method for predicting properties of pure material and also for mixture is the group contribution method. For pure materials, we have the Joubert correlations, where you break the molecules into different groups. We give it the number of groups, and we use some predetermined functions so that we can predict our properties as a function of the additions of different groups and accounting for the group effect. So in this case, the structure is represented by a vector which consists of the number of different groups. And F is a given function, and the development of QSPR is just a parametric regression of the model. A second generation of QSPR is what we call a machine learning QSPR. In this type of model, we have a structural robotic, and from that structure, we curate some kind of molecular features. It can be the molecular weight or dipole moment or whatever. Okay, and we use this feature and go through a machine learning model and predict our properties. And for example, we can use a neural network, and the key is that if we use a machine learning model, F would be a free-form function. Okay, so we are actually doing a non-parametric regression in order to build the model. Okay, but the problem with this type of machine learning QSPR is that human intelligence is still required to curate the proper molecular features of what we call the molecular descriptor that can successfully produce a QSPR. So we are now in the third phase of artificial intelligence. We have the wave is called a deep learning wave. The key properties of a deep learning wave is that we can treat data regardless of whether it's different form. We can build the functions of data of different forms, be it a graph, a text, or a video or audio. Okay, we can build functional relations between different types of data. So what we are asking is that, can we forget about features curation? We can just put in some form of data structure representation and obtain a deep learning QSPR to predict properties. Actually, we have tried this. One form of representing molecule is called SMART. Is simplified molecular input linear entry system. So every molecule is converted into a string of text, okay? And that is sufficient for us to capture the structure of molecules, but it does not contain the detailed 3D information. Somebody says that SMART is a 2.5D representation of molecules, but we don't know about that, but this is what is a text. So in our previous work, we have used this method to use this representation to develop a deep learning model that can produce what is known as a sigma profile, which is the charge density distribution on a molecule. It is also a very common method. Given this sigma profile, we can use what is known as Cosmosec or Cosmo RS to predict the solvent properties. Okay, so this is what we have done 3 years ago, and a modified form has come out this year. But SMART is only a 2.5D representation. So a more detailed representation of the molecular structure can be represented by the point .mol file. It contains the actual 3D structures with the locations and the type of atoms that is in the molecule. And in this, we have a public domain software that can easily convert SMART into this .mol file. And with this .mol file, it actually can convert the .mol file into a graph. A graph is what? Is a connection of vertices and edge. But this particular method that we can produce a molecular graph from the SMART or the .mol file. The molecular graph would consist of a set of vertices which describe the atoms that occupy these vertices. And then there are different features on the atoms, okay? And between the vertices are the edge, which is actually the bonds between the atoms, and we can also create a set of features for the edge. So the vertex and the edge forms a matrix, and the matrix, each of the matrix entries will contain a set of features that supposedly will describe the molecule completely. So in order to produce prediction, we use what is known as the MPNN model. MPNN model is a very popular model, and it has been very popular in predicting chemical properties from chemical structures. Okay, what it does is to integrate the edge features into the atom features in a repeated manner, and then eventually it will produce summarized versions the edge and the vertex properties. But in order to develop using graph to predict properties, we have to obey a rule, because the graph is represented by a matrix, but the ordering of the matrix should not affect your prediction. Okay? We can name this molecule as number 1 molecule. We can do the same as to name this molecule as number 1 molecules. The orders in the matrix should not affect your predictions. Okay? So we want to have a QSPR that the two types of representation will give the same predictions. To do that, there are standard methods to ensure that. One very popular model is the set-to-set readout. To do that, what is known in the graph network is we use what is known as a readout function, which is produced, which actually summarizes all the graph output into an input that is irrespective of the order of the matrix. And one popular readout is called the set-to-set readout, and somebody just sum the graph output, and it's a very simple, what we call the simple or naive readout functions. So in this work, we compare two different methods, MPNN with a set-to-set readout, and then followed by a deep neural network. And also we have the simple sum readout followed by the DNN. But also, if we want to investigate whether we need the MPNN, so we just drop the MPNN in front and use the readout function to read the graph and then follow it by a DNN. And for comparison, we'll compare with previous text-based models that we have developed. And also, we use a technique called selective sampling when we train a model. Instead of training a whole batch of training data, we train the training data, only a part of the training data, and then check whether the model can predict the other parts of the training data. And then if there are samples in the other part of the training data that is very poor, then we will incorporate them into the next training phase, and then we repeat the training phases. So this is the prediction of solubility parameters. Actually, we also investigated solubility parameters and other properties. The selective sampling is very effective when we try to predict solubility parameters. So if we compare the model, we look at sigma profile prediction, solubility parameter predictions, and we also look at a bunch of other properties, such as homo-LOMO, electronic properties, dipole moment, heat of formation, and standard enthalpy and standard entropy. Okay? I have ranked our model, evaluate our model using R², but of the training data, as well as we will compare all 6 of these models. Okay, so if the model is very good, it will be ranked number 1, and if the model is very poor, it will be ranked of a very high value. So if we look at all the properties, we sum the rank together, a model with the lowest rank sum will be the best model. So if we look at that, MPNN with the sum, with a simple sum, followed by a DNN is the best model we can get. We got, okay? And of course, if you look at all four of a graph-based model, they are much better than our text-based model. Okay, they perform much, but the best one. But instead of using a very elaborate real function called a set-to-set, we think that a simple sum is good enough. So to our conclusion, we have developed a graph-based deep learning QSPR. RP is missing. We use molecular graph as our input, and we can predict sigma profile, solubility parameters, or other point molecular properties predictions. They are much better than the text-based QSPR. QSPR we have developed using smiles as an input. This is natural because we included more information than a simple smiles representation. But we find that an elaborate readout is not necessary. A simple sum readout should be good enough. Is good enough for our purpose. Okay, thank you for your attention. And questions are welcome. And we also like to thank our granting fund granting authority for that research.
Thank you, Professor. Now floor is open for questions.
So I just want to know like limitations of smiles, like and if there are any kind of limitations on the side of molecule structure, and the second question is the follow-up question. Basically, how we are the smile is working on the structure. Is it just taking the reference as a center atom, or we are just taking the reference by atom to atom?
In the smiles representation, there's no center atom, but it has a beginning atom. Okay, so there is a rule that you go from right to left, but smiles is a standard representation. So there are many smiles, but there is what is known as a canonical smiles. Okay, so you can only represent the structure of a molecule by canonical smiles. Without representation, the molecular graph, there's no need of specifying which molecule we start with. Okay, because we ensure that the order of the matrix is irrelevant. Okay?
For this, we have first question was what is the size? Is that size of the molecule will matter, or the size does not matter?
The size should not matter, but we have been looking at small molecules only. We haven't looked at polymers yet.
Okay, polymer is so bigger in size.
Let's say if you have bigger large molecules, we have done some di molecule. Okay, consists of say 50 atoms or something like that. Okay, but it still works, but we haven't looked at much larger molecules.
If there is an isomers, how you deal with it?
Isomers will be accounted for in our molecular graph because of the information on the bond. Okay, but for predictions of properties like solubility parameter and sigma profile, usually isomer does not matter very much. Okay, but if we have a property that depends on isomers, the structure of the isomer is incorporated in the molecular graph. Okay.
So you mentioned the representation format called .mol files, right?
Yeah.
Which includes the 3D coordinates of each of the atoms. So
Yeah.
when we convert the .mol file to a graph, are we losing out on some information in terms of the 3D orientation of the atoms?
Maybe, we don't know. But actually it is possible to use the .mol file directly. But we found that a graph is a much easier way to go. Okay, we can just read in the .mol file as a representation and develop a QSPR model that way. That is also possible. Okay.
Thank you.
One question from my side. Your results are good. R-square values are also good. Are you looking for improving these results?
Of course, we will be looking at improvement of the results. Okay. Actually, we are looking at activity coefficient prediction using using this type of using the sigma profile we have developed. So how does it compare to activity coefficient using sigma profile produced directly by quantum mechanical calculations? We found that in our model, our predictions are inferior, especially for hydrophobic molecules. We don't know why, but we are looking at